In the vast blue expanse of the Indian Ocean lies an island steeped in mystery, Christmas Island. For centuries, sailors and explorers who landed on its shores told strange tales. They spoke of giant, shadowy creatures that scuttled through the dense jungle under the pale light of the moon. They described them as ghosts of the forest floor, powerful enough to vanish with a fallen coconut, leaving only tracks in the soft earth. We can find these stories in old ship logs and weathered journals, filled with a mix of fear and fascination. One entry from a 19th century naturalist simply reads, "A monstrous land crab of a surprising bigness that can climb trees." These early accounts were often dismissed as tall tales, the product of tired minds and tropical fevers. How could a crab, an animal we associate with sandy beaches and gentle tides, grow to such a size on land? It seemed to defy the very laws of nature as they were understood. The creature was given a name that matched its reputation, the robber crab, or Burgess latro. It was believed to be a thief, stealing not just coconuts but anything shiny or edible left unattended by visiting ships. These stories painted a picture of a cunning, almost mythical beast, a legend whispered among seafarers. But this creature is very real. Today we know it as the coconut crab. It is the largest land-living arthropod in the world, a true giant of its kind. Imagine a crab so large it can span nearly a meter with its legs, and so strong it can lift objects weighing over 28 kilograms. These are not legends, they are documented facts. The archival footage we have from early expeditions shows these magnificent animals in their natural habitat, dwarfing everything around them. Their sheer presence is awe-inspiring, a living relic from a time when giants roamed the earth. Yet, even with this knowledge, the mystery remains. The old sailors' questions are now our own. How can a creature with an external skeleton support such immense weight on land? Where does it get the astonishing strength to crack open a coconut, a feat that would challenge a human with a tool? The tales of the past have set the stage for a modern scientific investigation. We will follow in the footsteps of those early explorers, but armed with a new set of tools. Our journey will take us from the dusty pages of history into the world of physics and biomechanics to finally understand this forest ghost. This film promises to reveal the secrets hidden within the coconut crab's remarkable body. We will move beyond the simple observations of its size, of its diet, to uncover the hidden engineering that makes it all possible. This is a story not just of what the crab does, but how it does it. We will explore the incredible physics that govern its life, the way it walks, the crushing power of its claws. It's a journey into a world of biomechanics, where biology meets engineering. We will show you this animal as it has never been seen before. Our investigation begins with a fundamental question. How did this crab grow so large? Most crustaceans are limited by the water that supports their bodies. On land, gravity is a relentless force. To overcome it, the coconut crab has evolved a suite of extraordinary adaptations. We will use stunning slow-motion photography to break down its every movement. See the intricate mechanics of its legs carrying its heavy body across the forest floor. See the raw power of its claws as they tear a coconut husk. We will peel back the layers of this living machine. Our team has set up a field laboratory in the field to analyze the crab's abilities. Here we measure its strength, study its anatomy, and record its behavior with high-speed cameras. These visuals bring the hidden world of the coconut crab to life. Imagine the immense force of its grip visualized as a glowing pressure map. Watch a three-dimensional skeleton model assemble piece by piece, revealing the architectural principles that give it strength. This is the level of detail we will explore. The story is one of survival against the odds, ingenious solutions from nature solving complex physical problems. The coconut crab is not just a curiosity, it is a masterclass in natural engineering. By journey's end, you will understand the connection between physics and evolution. We will answer questions since those first explorers set foot on Christmas Island and reveal the superpowers of this incredible animal. How exactly does a coconut crab move its massive body with such apparent ease? What gives its claws a grip force 10 times stronger than a human handshake? And how does it survive on land, breathing air, when its ancestors lived entirely in the sea? These are the core scientific questions that will guide our documentary. To answer them, we will not rely on speculation. We will turn to the clear and universal language of science, mathematics, and physics. Our mission is to make these complex principles accessible and exciting for everyone. Don't worry, you won't need a degree in physics to follow along. We promise to use simple mathematics and clear, easy-to-understand diagrams to explain the science. When we talk about force, we will show you what it means in terms you can relate to. When we discuss leverage, we will use visual aids to demonstrate how a small movement can create immense power. Our goal is to equip you with a new way of seeing the natural world, to appreciate the elegant physics that underpins the existence of every living creature, especially this one. Throughout this film, you will see our scientific toolkit in action. We will use free body diagrams to show the forces acting on the crab as it walks. We will use free body diagrams to show the forces acting on the crab as it climbs. We will explore simple scaling laws to understand why an ant can lift many times its body weight, but an elephant cannot. These same laws explain how the coconut crab pushes the limits of size for a land-based arthropod. We will look at the material properties of its exoskeleton, treating it like an advanced composite material engineered for maximum strength and minimum weight. This journey is about discovery. It's about looking at a familiar, if formidable, animal and seeing it through the lens of science. By breaking down its abilities into fundamental principles of physics, we can gain a much deeper appreciation for its evolutionary journey. We will see that the coconut crab is not a monster or a ghost, but a finely tuned biological machine, a testament to the power of natural selection. So join us as we unlock the secrets of the coconut crab's superpowers, explained with the undeniable logic of physics. The story of the coconut crab begins not on land, but in the vast, life-giving ocean. Like all crabs, its distant ancestors were purely marine creatures, dependent on water to breathe, dependent on water to move, dependent on water to reproduce. They were part of a sprawling dynasty of crustaceans that colonized the world's seas for hundreds of millions of years. But at some point in its evolutionary history, one lineage of hermit crabs began a remarkable journey. It was a journey that would take them out of the relative safety of the water and onto the challenging, gravity-bound world of the land. This transition was one of the most significant leaps in the history of arthropods. This was not a sudden event, but a slow, gradual process that unfolded over countless generations. Early ancestors likely lived in the intertidal zone, the area between high and low tide. Here, they would have been exposed to the air for short periods, forcing them to adapt. We can see echoes of this lifestyle in other land hermit crabs today, which still return to the sea to release their eggs. The coconut crab's ancestors took this a step further. They ventured deeper into the coastal forests, a new frontier filled with both opportunity and danger. This move demanded a complete overhaul of their anatomy and physiology. One of the most critical changes was in how they breathed. Marine crabs use gills to extract dissolved oxygen from the water. On land, gills are almost useless as they collapse and dry out. The coconut crab's ancestors developed a unique solution, a branchiostegal lung. This is not a true lung like ours, but a modified gill chamber lined with blood vessels that can absorb oxygen directly from the air. This adaptation was the key that unlocked the terrestrial world, allowing the crab to sever its ties with the ocean for all but the very earliest stage of its life. It was a biological invention of profound importance. This evolutionary leap set the stage for the coconut crab to become the giant we see today. Freed from the constraints of a fully aquatic life, it could exploit new food sources and habitats that were inaccessible to its marine relatives. The forest floor offered an abundance of fallen fruit, carrion, and, of course, coconuts. But this new life also came with new challenges. Gravity became a constant enemy, and the threat of drying out was ever present. The anatomical features we will explore next are all solutions to the fundamental problems of living a life on land, a life that began with a single, bold step out of the sea. At first glance, the coconut crab's body plan seems familiar. Well, it possesses the classic arthropod blueprint: a tough external skeleton, a segmented body, jointed limbs. But upon closer inspection, its anatomy reveals a creature exquisitely adapted for a terrestrial, heavyweight lifestyle. The body is divided into two main parts: cephalothorax, fusion of head and thorax, houses organs and powerful leg muscles, protected by a thick, calcified shield called the carapace. Abdomen, soft and tucked underneath the body, a remnant of its hermit crab ancestry. 10 powerful legs arranged in 5 pairs. First pair, enormous claws, or chellae, defense, feeding, communication. Second pair, strong pointed walking legs, weight-bearing. Third pair, strong pointed walking legs, support and propulsion. Fourth pair, smaller, with tweezer-like pincers, delicate tasks, and juvenile shell gripping. Rearmost pair, tiny, hidden within the gill chamber, clean the breathing organs. This arrangement is a masterpiece of functional design. From the crushing power of the front claws, to the delicate cleaning action of the rearmost legs, the entire system works in concert. It allows the crab to thrive as a terrestrial giant. A large adult male can have a leg span nearly a meter, over 3 feet. Body weight can exceed 4 kilograms, about 9 pounds. The larger claw can reach over 20 centimeters. These numbers define the crab's physical parameters. These dimensions will be crucial when we later get into the physics. The coconut crab's primary defense and structural support system is its exoskeleton. This is not a passive shell, but a complex, multi-layered suit of armor that grows with the animal. It is a biological marvel, a composite material made primarily of a tough, flexible substance called chitin, which is reinforced with hardened proteins, and mineral salts, particularly calcium carbonate. This combination gives the exoskeleton both strength and a degree of flexibility. It is strong enough to protect the crab from predators and the environment, yet light enough to allow for movement. It is the crab's personal fortress, skeleton, and skin, all rolled into one. Unlike its marine relatives, the coconut crab's exoskeleton has special adaptations for life on land. The outer layer is waxy, which helps to reduce water loss, a constant danger for a terrestrial animal that breathes air. But the most important adaptation relates to its sheer strength. To support its heavy body against the unyielding pull of gravity, the exoskeleton is exceptionally thick and highly calcified, especially on the legs and the main body shield. This process of adding minerals, known as biomineralization, turns the chitin framework into a structure with material properties comparable to some engineered ceramics, providing immense compressive strength. Think of the crab's legs as hollow tubes. In engineering, hollow tubes are known to be incredibly strong and lightweight for their size, providing excellent resistance to bending and buckling forces. The coconut crab's exoskeleton exploits this principle perfectly. The thickness of the exoskeleton is not uniform. It is strategically varied across the body. It is thickest in areas that bear the most stress, such as the lower parts of the walking legs and the powerful joints of the claws. This is a highly efficient use of materials, adding strength precisely where it is needed most, without adding unnecessary weight elsewhere. This incredible suit of armor, however, comes with a significant trade-off. The rigid exoskeleton cannot grow. In order to get bigger, the crab must periodically shed its old skeleton and grow a new, larger one. This process, called molting, is a time of extreme vulnerability. We will explore this dangerous phase of the crab's life later on. For now, it is enough to appreciate the exoskeleton for what it is: a sophisticated piece of biological engineering that solves the fundamental problems of support and protection for the world's largest land arthropod. It is the very foundation of its physical prowess. While the exoskeleton provides the structure, the real engine of the coconut crab is its powerful muscular system. Hidden inside the hollow tubes of its legs and claws are massive bundles of muscle tissue. These muscles are what enable the crab to walk, climb, exert its phenomenal crushing force. The arrangement of these muscles is key to their effectiveness. Long muscle fibers run the length of each leg segment, pulling on internal attachment points called apodomes. This system of internal levers allows for powerful contractions, translating muscle force into movement at the joints. The muscles in the claws are particularly impressive. The larger claw, the crusher, is filled almost entirely with a single, massive adductor muscle. This is the muscle that closes the claw. Its sheer size is staggering compared to the rest of the body. When it contracts, it pulls on a wide, flattened tendon, which acts like a lever to slam the claw shut with incredible force. The physics of this lever system provides huge mechanical advantage, multiplying muscle force into the bone-crushing grip. All that muscle power requires huge energy, and energy needs oxygen. That brings us to the crab's unique breathing apparatus. The branchiostegal lungs sit inside the large gill chambers, on either side of the cephalothorax. These chambers stay moist and are ventilated by rhythmic beating of special appendages. The inner surface is covered in thin, cauliflower-like tissues rich in blood vessels, creating a huge surface area for gas exchange. This structure efficiently extracts oxygen from air, supporting slow, deliberate movement. But it has limits. It's not as efficient as mammal or bird lungs, so the coconut crab can't sustain high-energy activity like running. Its metabolism is tuned for a slow, steady pace. That's why it often seems lethargic, resting long between bursts of activity. It's an energy conservation strategy for an air-breathing giant that needs a steady, carefully managed oxygen supply. Its strength lies in power, endurance, over speed.